A gluon serves as an intermediary for the potent force binding quarks together, as an elementary particle devoid of mass. Functioning as the exchange agent in the strong interaction, gluons, as massless vector bosons, possess a spin of 1. They engage in the strong interaction, amalgamating quarks into clusters in agreement with quantum chromodynamics principles, configuring entities like protons and neutrons. Gluons bear the color charge characterizing the strong interaction, actively engaging in and facilitating the process. This complexity arises from the color charge carried by gluons, distinguishing quantum chromodynamics from quantum electrodynamics, featuring the uncharged photon. Coined by Murray Gell-Mann in 1962, the term gluon draws a comparison to a binding agent akin to glue upholding the nucleus. Together with quarks, these entities were denoted as partons in the scientific discourse by Richard Feynman. The gluon is classified as a vector boson with a spin value of 1 h-bar. Unlike massive spin-1 particles that possess 3 polarization states, gluons, as massless gauge bosons, are restricted to 2 polarization states. This restriction is due to the necessity of their field polarization being transverse to their direction of motion because of gauge invariance. The principle of unbroken gauge invariance dictates that gauge bosons must have 0 mass in quantum field theory. Experimental evidence indicates that the rest mass of a gluon, if it exists, is bounded to be under a few mega-electron volts per c². Intriguingly, gluons exhibit negative intrinsic parity. In quantum chromodynamics, QCD, there exist 8 distinct types of gluons. This contrasts with the photon in quantum electrodynamics, QED, or the 3W and Z bosons in the weak interaction. Additionally, gluons are influenced by the phenomena of color charge. Quarks carry 3 kinds of color charge, while antiquarks bear 3 types of anticolor. Notably, gluons transport both color and anticolor, creating 9 possible color and anticolor combinations in gluons, including red anti-Erd, RR, red anti-green, RGG, red anti-blue, RB, green anti-Erd, GR, green anti-green, GG, green anti-blue, GB, blue anti-Erd, BR, blue anti-green, BG, and blue anti-blue, BB. These combinations represent effective states, distinct from the actual observed color states of gluons. To comprehend how these states combine, a deeper dive into the mathematics of color charge is necessary. Strongly interacting particles like hadrons, e.g., protons, neutrons, are perceived to be colorless or in a color singlet state, analogous to a spin singlet state. The color singlet state, open bracket, R, R bar plus B, B bar plus G, G bar, close bracket, divided by the square root of 3, permits interaction with other color singlets exclusively. This emphasizes the non-existence of gluons in a singlet state due to the absence of long-range gluon interactions. In contrast, a set of 8 independent color states known as the color octet correspond to the diverse colors of gluons. These states can be amalgamated in multiple ways and are commonly represented as linearly independent entities separate from the singlet state. Notably, the gluons are presented as vectors in the adjoint representation of color, SU Center 3 group. This representation is pivotal in understanding the fundamental properties and behavior of these force carriers in the realm of quantum chromodynamics. Gluons play a crucial role in strong interactions due to carrying color charge. These gluon-gluon interactions result in the creation of flux tubes, which are responsible for confining quarks within composite particles known as hadrons. This confinement limits the strong interaction to a range of approximately 10⁻15 meters, restraining quarks within nucleon-sized distances. As the distance between quarks increases, the energy within the flux tube rises linearly, leading to the creation of quark-antiquark pairs or exotic hadrons rather than elongating the flux tube. Gluons, being integral to hadron confinement, are not directly engaged in nuclear forces. Instead, these forces are mediated by mesons. While in the typical phase of quantum chromodynamics, QCD, individual gluons may not travel independently, there is a conjecture about the existence of glue balls entirely composed of gluons. Beyond this phase, at extreme conditions, quark-gluon plasma emerges, where quarks and gluons function as free particles. Experimental investigations have revealed the manifestation of quarks and gluons by fragmenting into more particles correlated in jets, a phenomenon observed in various collider experiments. The spin nature of gluons was confirmed through multiple experiments during the late 1970s and early 1980s, solidifying their importance in strong interactions. Studies at particle colliders such as HERA at DESY have provided insights into the distribution and contribution of gluons in protons. The verification of color confinement has been demonstrated through the absence of free quarks, emphasizing the prevalence of quark-antiquark pair production to maintain color and flavor numbers. The existence of quark-gluon plasma, representing a new state of matter, was initially claimed in heavy ion collisions at CERN SPS in 2000 and further confirmed by experiments at RHIC and LHC in subsequent years.